Here we want to solve the Euler's ODE. This is the case, and A must not be 0. Okay, so we let y be just, let's say, t raised to some number r be a solution. Now we can plug this into here. Then to plug this into here we need y prime, sorry, this is y prime, and we need y double prime. This is y, then y prime is by power rule rt r minus 1, and y double prime is r minus 1 t r minus 2. Now the ODE becomes a t squared y double prime, which is here r minus 1 t r minus 2, plus bt y prime, which is r t r minus 1, plus cy is t raised to r equals 0. Okay, so when we do this we need to assume t positive, and we can do the same thing when t is negative. So let me add here, when we assume this, t must be positive. Okay, here we can combine these two factors, then this is r, sorry, I meant this t. So t squared t raised to r minus 2, so this is just t raised to r. Here t raised to 1, t raised to r minus 1, so t raised to r, and we got t raised to r here. So from these three terms we can factor t raised to r. That leaves a, this is gone, r minus 1 plus br plus c equals 0. Since t is not 0, then t raised to r is not 0. So this factor not 0 means this must be 0, because we got a product of two things 0. So ar times r minus 1 plus br plus c equals 0. And this is sometimes called the characteristic equation of this Euler's ODE. Okay, now this is a, when we distribute a r squared, so this is a quadratic degree 2, okay, equation in r variable. The variable is r and degree 2 quadratic equation. So when we solve we get three different types of r values, so three cases. As we saw in algebra, when we solve a quadratic equation, then the answers, the roots, are real distinct. Case 1, the roots means r values. Okay, that means r values. Roots are real and distinct. So in this case, there will be two r values, so r is r1 and r2. In this case our solutions are just, if we go back, what is the solution we assumed? T raised to r. So we get two solutions, t raised to r1 and t raised to r2. Then t raised to r1 and t raised to r2 are two linearly independent solutions, because r1 and r2 are different. Okay, two linearly independent, okay, linearly independent solutions. That means these two solutions form a fundamental set of solutions. So the general solution thus a general solution or the general solution, doesn't matter, is y equals, as a function of t equals constant c1 first solution plus c2 second solution. Okay, that's the easiest case. But when we solve this quadratic equation, we might get equal roots. Okay, so r will be just r1 and r2, both same. There will be two roots, but they are same as r. Let's say I'm just writing r. Then one solution is easy, just as we said, y equals t raised to r. So y1 is just t raised to r1, but that's also r. Now the second solution will be t raised to r again, but they are linearly dependent because they will be the same, so that's not good. Then it can be shown, so I'm not going to go through all the steps, but we can find a second solution we just multiply by natural log. It comes out to be natural log of t times t raised to r. In fact, if you plug this into the original ODE, go up, then this is also a solution. Okay, we can easily check. If you plug in this function, a product here, then we get 0. Okay, that will be a solution, and obviously this is linearly independent with this, so this set, these two solutions form a fundamental set of solutions, and thus in this case the general solution y is a function of t is c1 first solution tr plus c2 second solution ln t and t raised to r, and our t is positive, so we don't have to put absolute value. And in fact we can factor, in this case we can even do better, we can factor t raised to r, so c1 plus c2 natural log of t. And the third case is the roots are complex conjugates, complex roots. So let the roots be rv lambda plus mu I, and these roots always come in pairs, so plus minus mu I. Okay, then a solution is just t raised to r. Y, let me just write y1, but y is t raised to lambda plus minus mu I. Okay, so we got complex roots here, so it's not good. I mean, we can write lambda plus mu I is one solution, and lambda minus mu I, t raised to lambda minus mu I, another solution, but it's kind of not good, because when we started the ODE, we did not have any complex numbers. Now we are getting complex numbers. So let's try to simplify and not write complex roots in this, complex solutions in this way. This can be separated as t raised to lambda times t raised to plus minus mu I. In fact, we can get a pair of linearly independent solutions just from t. Okay, we can take just positive t raised to lambda times t raised to mu I. So I'm going to work on this part, this factor, and from here I'll be able to get two real solutions, okay, in this way. So I'm going to apply the following rule. So when we have x, that's same as e raised to natural log of x, because e and natural log, their actions cancel, and we get this. Okay, and I also want to remind you, when we have e raised to I theta, this is from trigonometry, it will be cosine theta plus I sine theta. That's another Euler's formula. Okay, so we have here t raised to mu I, which is same as e raised to natural log of mu I, using this fact. Oh, my bad here. Okay, t raised to mu I, e and natural log cancel, so we just have this. But this is exponent, so this can be pulled to the front. So this is same as e raised to, bring this to the front means here, e raised to mu I ln t, and our t is positive, so we are good. And this is same as e raised to I mu ln t. Now this matches with this ei theta, which is cosine of mu ln t plus I sine mu ln t. Oh, this is a linear combination of two things, two functions. In fact, each part is a solution. So if we go back here, t raised to lambda times this part, I just took plus sign, that would work. We could have taken negative and get the same place. So solution y is t raised to lambda times, second part is this, cosine mu ln t plus I sine mu ln t. That's the solution. And when we distribute from here, we can get two solutions. y1 t lambda cosine mu ln t, and y2 be just t lambda. This is a constant, kind of, this is a linear combination of two solutions. Okay, so t lambda this and t raised to lambda sine, and these are obviously linearly independent. So the general solution when the roots are complex is y equals c1 first solution t raised to lambda cosine this plus c2 t raised to lambda sine mu ln t. This is it. Or we can do better, we can just factor t raised to lambda out, c1 cosine mu lambda t plus c2 sine mu lambda t. Okay, this is how we get the general solution, final.